Hi, welcome back. In this lecture, I would like to introduce an important quantum gate. That is a quantum gate that is operating on a 3-qubit system called CCNOT. As the name says, it's an extension of the CNOT operation that we've seen before. It's basically adding one more control qubit to operate. This quantum gate is also widely known as a Toffoli gate, so we will hear often about the Toffoli gate. In addition, I'm going to introduce the swap quantum gate. This is operating on 2 qubits and is control version. That is a control swap or Fredkin gates. But let's start with the first CCNOT. So CNOT is also called the Toffoli gate. And what is the working principle? Multi-qubit conditional operation can be made even more selective by performing operation condition on more than 1 qubit. So for instance, here we have an example of the so-called CCNOT or Toffoli gate. We have our target gate that we know from CNOT, in this case is a NOT, and then we have not only one control qubit but 2 control qubit. In order to have this NOT operation on the target qubit, both conditions need to be 1. So the Toffoli gate or the CCNOT gate is basically just to generalize the CNOT operation by adding multiple conditions. A CNOT with the 2 condition qubits is commonly referred as a CCNOT, also called the Toffoli gate, from the name of the inventor in the classical computing. It turns out that it is also a reversible classical gate. By far, CCNOT is one of the most important QPU operation. We will see in the next module that multiple CCNOT can be combined in cascade to produce a wide variety of logic functions in quantum computing. So these slides represent a summary of different quantum gates operation, NOT, CNOT, and CNOT, and CCNOT. And you can see that the CCNOT version is just a more selective version of CNOT. So CCNOT can be interpreted as an operation implementing if A and B, where A and B are the control qubits, must be true, then flip C, that is our NOT operation. We can express the CCNOT operation using also a matrix form. We know that the second and the third qubit need to be equal to 1 in order to have a NOT operation. So the matrix form is basically identity matrix, right? When the qubit 2 and 3, when the binary representation of qubit 2 and 3 is 1 or 0. In the case that the second qubit and third qubit binary representation is both 1, 1, because this is control, then we have a NOT operation. Obviously, they also can be represented as in-place operation, basically just swapping the complex number corresponding to the state that we need to swap as a target qubit. I want to introduce also an important operation that is a swap, also called exchange, that basically just exchange 2 qubits. It turns out that in many cases the architecture doesn't support the swap operation. So if the architecture of a QPU allows, then a swap is quite important operation in which the physical object representing qubits are actually moved to swap their position. Alternatively, a swap can also be performed by exchanging information contained in 2 qubits using a combination of other quantum gates. Particularly, we can use 3 CNOT operation. So this is the symbol for the swap operation. So it's 2 cross and then a line. And we can realize also a swap operation as a combination of CNOT as it is on this slide. The swap has also a matrix formulation. Is basically we are swapping the two values when the input differ in the binary representation. If the input they don't differ by binary representation, that we have just identity matrix. We can also show that the equivalence between swap and the swap using a combination of 3 CNOT by doing this in place operation. Right, so we applied 3 CNOT and we obtain basically the swap operation. On a QPU, the swap comes into its own when we consider generalize it to a conditional operation called CSWAP or conditional exchange or conditional swap. It's not a surprise that a CSWAP can also be implemented using 3 CCNOT gates or Toffoli gates. You see here the equivalent circuit. If the condition of a qubit for a control swap operation is in a superposition, then it becomes very cool. So we ended up with a superposition of our 2 qubits being exchanging and also not being exchanging. So it's very very interesting effect. Also, CSWAP can be written in a matrix form. So whenever the control qubit is in a 0 state, then there is no operation, and we have the identity matrix. In the case that the control qubit is in 1 state, like here, then we have the swap tensor formulation. This is the last slides, and talk to you soon.